Hi, my name is Sadman Binzaman. This is EL6303, assignment 12, question number 1. Given the LTI system, we're expected to suppose that x of t is wide sense stationary. Well, we're asked to show that y of t is also wide sense stationary. First of all, I think it's important that we just review what wide sense of stationary means and the properties associated with it. First of all, we know that when a stochastic process is defined as being wide sense stationary, the expected value, or the mean of that process, is a constant. And the autocorrelation depends only on tau, which equals to t1 minus t2. So the expected value of x of t we know equals some constant eta of x. And the autocorrelation of x is defined as the expected value of xt1 times the product of xt1 and xt2. We also know that y of t is So we know that y of t is defined as the convolution between x of t and some impulse response h, or h of t, which equals the integral from negative infinity to infinity of xt minus tau times h of tau d tau. For the output y of t to be also wide sense stationary, we also need to prove those same 2 points, those properties, mainly that the mean of y of t is a constant and the autocorrelation of y depends only on tau. So we know that the expected value of y of t equals the expected value of the convolution of x of t and that impulse function. And so the expected value of y is the same thing as saying the expected value from the integral from negative infinity to infinity of xt minus tau times h of tau d tau. We can basically rearrange that. Remember, the expected value only really applies to the random variable x, so we basically have the integral from negative infinity to infinity of the expected value of xt minus tau, which we know previously, since x is wide sense stationary, would equal some constant h of tau d tau. We could take out that constant, so we're left with eta of x, which we had the expected value basically equate to eta of x times the integral from negative infinity to infinity of h of tau d tau. That integral also evaluates to a constant. Well, basically what happens is we're asked to remember the frequency response. Basically we set h of omega equal to 0. Remember, h of omega, the frequency response is defined as the integral of h of tau multiplied with e to the negative j omega tau d tau. So we basically, what we have previously is the integral from negative infinity to infinity of h of tau d tau. So basically what we're missing between that and the frequency response is that e of negative j omega tau. The only way we could really, we could easily deal with that by assuming that omega equals 0. So obviously if omega equals 0, that exponent e to the negative j omega tau simplifies to e to the 0 power, which is equal to 1. So basically we're left with, what we have the expected value, the mean of y equal eta x, which was a constant, times another constant, which produces a constant. So we proved that first property. Now the second property, where we're asked to show that the autocorrelation is also a function of tau. So we know that the autocorrelation is the expected value of the integral of h of s x t minus s ds times the integral of h of r x t plus tau minus r dr. We can rearrange those integrals, so we basically have the expected value of the integrals, double integral of h of s, h of r, xt minus x, xt plus tau minus r ds dr. Again, remember the expected value really only applies to the random variables of xt minus x and xt plus tau minus r. That over there evaluates to the autocorrelation of x of t plus s minus r. So we have the double integral of h of s, h of r, the autocorrelation of x, t plus s minus r ds dr. And that, we could just call it some function of tau. Again, we proved that the autocorrelation of y is a function of tau. So since the autocorrelation is a function of tau and the mean of y of t is a constant, we can safely determine that y of t is also y times stationary. Thank you.